So we were talking about exponents. We were trying to refresh a little bit on what exponents are. We're trying to play the game of no rules. No rules at all. Anytime you use a rule in this class, you are running a big risk that I will catch you, right? Because my job is to develop within you good thought. If you are not having thought and are instead trusting somebody else's thought, then you are not training to be a professional who can contribute to the conversation, right? So no matter what field you're going into, if you want to be somebody of value, you have to be able to contribute original ideas, or at the very least, be able to explain other ideas that your audience hasn't heard. But that at no point should we ever be broadcasting things we heard before, regardless of what authority told us to do that, especially not if the consequences are quite real. And so in this class, like, this is a chance to practice that ability, that people are going to trust you as a point of authority after you enter the real world in your career. Do not have them trust through you, your high school, middle school, or even college math teachers. We make mistakes. Not to mention, nobody can backtrack that, and it's still going to come down on your head. So you've really got to be able to explain everything from a place you understand it. And if things are ever not being explained in a way that you can explain to somebody else, then that's a point for conversation. And I've made it my goal as a teacher to be able to have an answer for every single question you all could possibly ask around these topics. Every single one, we will make it make sense. Not from an I told you so. I call that proof by intimidation. Me being up here is not a really big deal. There are plenty of people who can stand in front of you and tell you things, please don't repeat them. Instead, we want to make sure it makes sense. So in that same vein, we're going back through exponents. We explored all those rules, realized they're just shortcuts towards a story of logic that you can explain to other people and make sense. Now, I want to show you that logarithms are no different. Real quick, from like super thumbs up to super thumbs down, if I say logarithms, who here knows what I'm talking about? Yeah, that's kind of like I would expect around here. I'm going to let you all know. Until I started teaching, I was right about here, maybe closer to here. I could do some practice problems, but if somebody asked me why those practice problems are correct or how it makes sense, anything along those lines, no idea. I can just push numbers and symbols around and reorganize pencil lead. Like, there's no thought, right? I want you all to leave here with an understanding of logarithms, because if you don't understand it, this is a wasted lecture. You will never use this information in the real world if it doesn't make sense to you. Because in the real world, there's no pushing of numbers around symbols for the point of just pushing numbers around symbols. There's stories here. It's useful stories. Really, really good models we're going to explore. So I got a quote. By shortening the labors using logarithms, a mathematician by the name of Napier doubled the life of the astronomer. This is something that was written by another mathematician about a mathematician named Napier. We're going to talk about Napier. Essentially, what this quote is trying to get across is that with the use of logarithms, astronomers, as well as anyone who is in the field of navigation and anybody who had to do long, difficult calculations, could do more calculations more accurately in less time. And so they essentially were producing more across their lifespan than they would have if they just had to use brute force. So logarithms are a shortcut. They're another shortcut. So let's talk about it a little bit. So let's talk about Napier. John Napier, Scottish mathematician about the 1550s. I'm not a huge history buff, but what I do know is that in 1492, Columbus sailed the ocean blue. So we're talking about a timeline that's right after westward expansion. We've got a lot of people going to sea for the first time and going across vast distances. Let's put that in perspective. How long do you think it would take to travel across the Atlantic Ocean in a ship, not motored? Couple months. Now, if I'm talking about being off in terms of navigation by a few degrees, that's the difference between me ending up in New York versus Central America, right? Like, big deal. And when you're talking about 2 months, it's going to take a lot longer to travel to Central America than it's going to take to travel to New York. And if you only got so much food on board, you better make sure you don't mess up your math because you're going to starve out in the middle of the sea and no one's going to know. Right? Big, high stakes, not to mention money. Oh my golly, you find some trade routes, you find a way of doing those trade routes quickly, money is happening here. So big deal, big motivation for mathematicians to introduce their skills into the real world. So what we're talking about is a bunch of people who are ship captains or ship navigators now having to do very intricate calculations with decimals, because decimals were going to be evident whenever you're talking distances. So let's try to do a quick example. Let's imagine that I've got these two decimals, 0.1234 and 0.5678. If I asked you to multiply those by hand, just imagine what that would look like. 5, 6, maybe 7 lines of work. Don't mess anything up. If you mess one thing up, the whole thing's gone, right? Difficult to do by hand. What about division? Oh my golly, long division with this? Are you kidding me? And like, we're college educated people. There was nothing that said that you had to be college educated to be a navigator on a ship. So we're talking about a difficulty between people who were employed and the skill set that they required. Now, on the other hand, if I asked you to add those, wouldn't adding those decimals be much easier? Right? You just down the row, maybe 2 lines of work, a couple of things to carry, and we're good. Subtraction, down the columns, a couple of things to carry, not too bad. So what Napier decides is he is going to look for a method of taking multiplication problems like this and finding a way to solve them with addition. Right? If he can change the numbers, do an addition problem, and then change the numbers back, he has found a way for people who have less mathematical skill to be able to do big calculations. And not only that, he gets to make a big old book of table references, sell that book of table references, and then make a lot of money. Because you know who has to do this? Everybody on the boat, everybody who's doing the navigations, everybody who is looking in astronomy and trying to find small minutiae and directions. Big money-making opportunity here. So what he comes up with is a large, dense, intricate calculation that he keeps very secret, because if he shared it with people, he wouldn't be able to sell his book, and gives it a big fancy name. He calls it a logarithm. So he comes up with these tables of logarithms. Logos coming from ratio, and arithmos talking about numbers. So he's got this big ratioing number process thing he is doing in his workshop, writing a book of reference tables, selling it to people, making lots of money. People are able to sail the ocean blue. What we're going to recognize is that as a result of him actually keeping it secret, other mathematicians couldn't look at it. And by the time we could look at it, it turned out it wasn't actually anything that special, that he had been making it way more complicated than it needed to be, because all he had been doing was really playing with exponents. And that's it. So we're going to go through that story. Let's do a prelude, if you will. I'm going to build within you another model. Remember the last time I talked about logarithms as power finder functions. I'm going to use that again, but I'm also going to give you a second thing. And the second thing, between both of those, I find them really good, easy models of math to keep up with the story. So let's do, for example, I'm going to introduce this idea of a logarithm. Logarithm is a fake logarithm, right? So I'm going to get to give you something. Don't take it too much to heart, but it's going to be a good example. So let's imagine that a logarithm, the entire job it does is it counts zeros. So for example, if I say, what is the logarithm of 1,000? That would be 3. There are 3 zeros in 1,000. If I say the logarithm of 10, that would be, all right, everybody, come on. How many zeros in the number 10? 1 0. Very good. Do we all feel like that's a pretty easy process? We all feeling pretty good? All right, what if I said the logarithm of 1,000,000? Logarithm of 10 million? This is not difficult, right? That's what I'm going to use as a model. Now, the challenge, of course, is that this is a very limited process, because what I want to instead compare is what happens if I start playing with not nice numbers. So let's get a few here. Let's do again. Logarithm of 100 is 2. Very nice. Ain't that easy? Ain't that great? That's good stuff. What about logarithm of 10? We said 1, very good. Logarithm of 1. Do we feel good on that? Excellent. Let's take this, let's extend the pattern a little bit. What about logarithm of 0.1? Ooh. Let's see a hand. Somebody justify what they would think. Go ahead. So we get this idea of kind of it being before. I wouldn't want to put 0 because I might accidentally think I'm talking about 1. And there's obviously a difference here. How can I capture this idea of there's a 0, but it's not after, it's before? What do you think? Could we try -1? Are we all good with that? Like if I say -1, that means not a 0 after, that means the opposite of a 0 after, that means a 0 before. So we can make this like maybe -1. There you go. Do you see? We're building math. We came up with a good model of logic. We're just creating things. We're exploring. This is how things are invented. What about the logarithm of 20? Like, yeah, we might want it to be like 1, but it's obviously different than plugging in 10. What would the logarithm of 20 be? Go ahead.
It'd be 1 regardless because it's only looking at the zeros.
Good. It could be if we chose it to keep it that literally. I want us to expand it though a little bit. If 20 is between 10 and 100, shouldn't the logarithm of 20 be something between the logarithm of 10 and the logarithm of 100? What do you think? 1.2? Sure, right? Maybe 1.1, maybe 1.2, something around there, right? Give me a general nod if we feel pretty good. If I was to say the logarithm of 20 is 1.1, because it's somewhere between the logarithm of 10 and the logarithm of 100. Okay, cool, excellent. You ready for the big reveal? I haven't been talking about logarithms this whole time. What I've been talking about is logarithms. But specifically, I've been talking about logarithms where I'm trying to count zeros of nice numbers that are in terms of 10. So really what these all are is these are all log base 10. Log base 10 of 100 asks for us to find the power that turns 10 into 100. What would that power be? 2, because I have 2 zeros. Because if I multiply 10 by itself, I get 2 zeros. That's an exponent of 2. That's a 10 times 10. What about if I did the log base 10 of 10? That'd be the power finder. I'm trying to find the power that turns 10 into 10. That would be 1. Nice. What about this one? I need to find the power that turns 10 into 1. That would be 0. What if I wanted to find the power that turns 10 into 0.1? -1, right? Because 10 to the negative first power would be 1/10, which is 0.1. So I've got this building, and here's the nice thing. Somebody with a calculator, tell me what log base 10 of 20 is. You should be able to type it in by just hitting the log button. If it doesn't say a base, it means base 10. 1.3? Does that make sense? All right, it's kind of near that 1.1 mark, between 1 and 2. Did you get something different?
No, I got something same.
You got something the same? It's that idea of saying it's somewhere between 1 0, which would be 10, and 2 zeros, which would be 100. Yeah, somewhere between there. Go ahead.
So why 1.3 specifically?
Because let's all do this in reverse, right? That means through this story, I found the power that turns 10 into 20. Let's all check this with our calculators. Do 10, and then for the exponent, put 1.3. Tell me what you get. 10 to the 1.3, what do you get? 19.9. So if you included all the decimals of that, instead of 1.3, it was 1.3 more stuff, right? If you included all that more stuff, it would be 20. It's the exact storyline. We're just flipping it. But this idea of counting zeros really makes it approachable, really gets us in of saying, oh, if I'm talking about base 10, I'm just talking about how close I am to the next whole magnitude of tens. We'll do some more examples. This is really a good opportunity. The reason I love this lecture is because it's a great opportunity to remember that mathematics is just a change in perspective. If we remember the week 0 videos, there was that idea of diving into the ocean and seeing the ocean from different perspectives, being able to describe it to each other. Well, let's remember that counting in tens is nothing special. Why do we count in tens? It's nothing to do with easier. Ask a child who has no idea how to count. They could not tell you why we stop. Why do we count in tens? There's a why. Think about it. How do you teach a child to count? There you go. It's on the fingers. We got 10 fingers. That's why we count in tens. Would it surprise you that other cultures count in 20s? Why would they count in 20s? Oh, we got our toes, right? Why would we only do our fingers? We have our toes. That would be so much easier. We could also count differently. Like, for example, how many hours are there in a day? 24. That's a weird number. Didn't we get to invent the clock? Why 24? That seems like a very random number. How many minutes are there in an hour?
60.
That seems like another very weird number. Why 60? Right? Why not 100? That would be easy to split it up. It's because it came from a culture that was counting in 12s. 12s. That's why there's 12 hours in the morning and 12 hours in the evening. That's why there are 5 groups of 12 minutes in an hour. That's why there are 60 seconds in a minute and 60 minutes in an hour. That's why there's 360 degrees in a circle. That's why there's almost 360 degrees or 360 days in a year. It's from a culture who decided to invent time navigation using counting of 12s. And you can all do this with me if you'd like to try it. So here's how we do the counting of 12s. Ready? We take both hands. We're going to count on our knuckles. So we're going to use our thumb. We're going to count 1, 2, 3 knuckles, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're going to hold up one group of 12. You do that over and over again, you'll get how many groups of 12? 5 groups of 12, which is 60. Exactly right. There's nothing special about ours. If you want even more proof, why is the number 11 not 1 teen? Right? We go 10, and then we go 11, 12, 13, 3 teen, 14, 5 teen. Why do we wait until we get to 13? Because it came from a Germanic root where the Germanic people were counting in 12s. So they had a different name for the first 12 numbers. Because we counted in 12s. Because there's nothing special about 10. Nothing at all. In fact, let's think about other ways we count. If we talk about binary, binary has how many digits? 2 zeros and ones, right? Computers don't understand the idea of 10. They don't understand it. They have to communicate 10 to us, and then we have to translate it from zeros and ones. So we could talk about computer math. We could do binary. We could do binary logarithms. So we could say, for example, what about 16? 16 in binary is 1, 0, 0, 0, 0. That's what it is. So I could ask, for example, what is log base 2 of 16? That means if I'm communicating with a computer, how many zeros does it think are in 16? 4 zeros, right? And let's double check. Is 2 to the 4th 16? I got a few people nodding and a few people just staring at me. Y'all got calculators, right? 2 to the 4th is, there you go. So in its language, it's counting zeros the same way we did in our language. That's logarithms. Logarithms is just counting of magnitudes, counting of the zeros in that culture. Let's do, for example, like we can look at the ancient Arabs. The ancient Arabs counted base 12s, right? That's what I was just telling you about. They were the principal mathematicians at the time when navigation and time were being pinned down. So they might say, what is log base 12 of 1,728? We don't want to look at that through our eyes for zeros. We look at it through their eyes for zeros. So through their eyes, they have one group of 12, and then 12 of those groups, and then 12 of those groups. What would be 12 times 12 times 12? 1728. because they're looking at groups of groups of groups, magnitudes of 12 on top of each other, over and over and over again, just like 1,000 for us is magnitudes of 10 on top of each other. So it's a chance to understand that like different cultures can do math too. And I think that that's awesome. What about applications? In terms of applications, logarithms come up whenever we don't want to have conversations about increasing from 10 to 11. And instead, we want to have conversations about increasing from 10 to 100 and 100 to 1,000 magnitudes, right? Zeros, putting zeros at the end of things. So we have to use it whenever we're talking about conversations that have really, really small values and very, very big values. For example, decibels. Do y'all know that decibels were logarithms? Like they are. So for example, if we look here, you got to crane in here a little bit, but this says whispering is 30 decibels. Now there's about 50 of you in here. If I had all of you begin whispering at one time, maybe we would think that I do 30 times 50. Well, 30 times 50 would be about 1,500. That means that you all whispering together is going to be louder than a jet engine. That's obviously not correct. You could all whisper just fine if we did some group work. So what's happening? It's because we first need to think about the 30 as being a way of talking about 3 zeros. Decibel has a little bit of off as far as like 30 means 3 zeros because they're trying to make it nice round numbers. But if I had now 50 of you all whisper at the same time, that would be 50 times of the number. And then we would take that 50,000, we would come up here where it's talking about tens of thousands, and we would relate it back. And it'd be about the sound of a large refrigerator. That seems more appropriate. So we're not talking about adding zeros unless that's the appropriate conversation. If I'm just adding whispers, we add whispers. If I want to talk about its magnitude, then I can count the zeros. But we've got this play between changing in terms of magnitudes and just changing in terms of our normal addition subtraction. Let me pause here for a moment. Any questions on logarithms and this whole idea of logarithms just being a counting of magnitudes? Go ahead.
Will this be in the guidance?
Yep, it's all up there. Good. All right. By the way, the Richter scale, earthquakes, do you all know that earthquakes are logarithmic? So if you hear somebody say that this is a magnitude 7 earthquake, that's how many zeros? 7 zeros. That's a lot of zeros. How much bigger is that than a magnitude 6 earthquake? Yeah, 1 0, but it's not 1 bigger, it's 10 times bigger. So whereas one thing might level a neighborhood, the other would level 10 neighborhoods or more. Right? We've got a big change. So whenever you hear on the news, you say like this was an earthquake. Like if you hear that number between, if it's 4 versus if it's 7, understand that's not a step of 3. That's a step of 1,000. That's 1,000 of those earthquakes together. All are combined in the bigger one. Say that again. Yeah, that's exactly what it was. Yeah, it's one earthquake 1,000 times stronger or 1,000 of those earthquakes all squished into the new one, right? I mean, that's the idea. We're talking magnitudes, jumps of magnitude.
Moral of the story, don't live on a fault line.
Fault lines are rough. Yes, agreed. All right, so let's start to pin some of this down with some example problems. Let's start to pin down this story and get to play with it. First, we have 2 logarithms that we will probably use the most. One is because most of the world does count in base 10, as do we, then we will call that the principal logarithm. In other words, if I don't specify the base, assume that we're just using our normal counting methods. So if I say, for example, what is log no base of 1,000, that would be what? 3. Right? Because we're assuming that we're counting in tens. Most of the world does count in tens. We count in tens. Let's just use that as the baseline. If I want to use something different, like if I say log base 2 of 1,000, don't count the zeros, right? We'd have to first translate this into computer speak and count the zeros. That's difficult. So instead, maybe we look at that through the lens of a power finder function, which is the exact same thing. And we just ask ourselves, what power would turn 2 into 1,000? It'd be the same number of zeros as a computer would think in their language. It's the same thing. We're just fluctuating between the two models. They're the same thing, just different stories. So if I don't specify, it's log base 10. However, we have another exponent that we said comes up a lot as a reference. What is the base that we invented in this class that we use as a reference for compound or exponential growth? E. Because E is so useful as a reference. Remember, it's the speed limit of growth, right? Because it's so useful as a reference, we have given that the term natural logarithm. So log base E is the natural logarithm because we will use it whenever we are trying to make equations that reference some other kind of speed limit. So if I say ln, ln comes from the Latin name of it, right? So we got Logarithmos naturalis. That's why it's ln instead of nl. But nonetheless, it's just a logarithm base E. It's asking E to what power gets me thing. It's still just a power finder function. Again, let me pause here for a moment. Does anybody have any questions about, again, how I'm sort of feeding this into a sentence, making this language so that we can talk about it? All right, so let's do, again, some examples here. What is log of 100,000? 6, right? If I don't say any base, we're talking about base 10. Base 10 you can look at as either the logarithm or you can look at as a power finder. Either one's the exact same answer. So this is going to be 6. Let's do, what's log of 10? 1. What's log of 10,000? 5. Good. My question to you all, how do these numbers relate? Ah, so that one's gonna be 5, and then this would have to be 4. Okay, so we gotta do a little correction.
Yeah, I was just about to say that, but
That's okay. My job is just to guide you all. You all give it momentum. How do these numbers connect? I like that one. And in fact, that one will be consistent. I mean, the other one I like too. That one will actually work out in the other problems too. So we're the focus on that one. Take a look. I don't want this to be a rule. I want this to be a combination of everything that was just shared. Doesn't it make sense that if you multiply the 1 0 thing times the 4 0 thing, you get a 5 0 thing? Doesn't it make sense that those zeros would add? So doesn't it make sense that I could look at this as saying the adding of the zeros happens when I multiply the things? Watch how we can write all that. Log of 10 is the zeros in 10. If I add that to the log of 10,000, that's 1 0 and 4 zeros gives us 5 zeros. The number of zeros that are in the log of 10 times 10,000. Because if you multiply 10 times 10,000, you will get the total zeros that are both in the 10 combined with the ones that are in the 10,000. This is our first logarithm property. If you are multiplying inside of logarithms, you can add the logarithms. Why? Because if I multiply inside, I build magnitudes, and the magnitudes build by taking the magnitude of one and combining it with the magnitude of the other. That's the rule. Well, shortcut, right? It's the story. It's just the story representing itself. Let's take a look at this one, for example. Log of 10 divided by 10,000. That would be, if we simplified it, log of what? 1,000th? 0.001. Let's remind ourselves that would be what? -3. Yeah, right? A 3 is zeros before the decimal. Or in other words, 10 to the -3rd gets us that. I'll be right with you. Give me a second. Log of 10 would be 1. Log of 10,000 would be 4. How do I use the 1, the 4 to get the negative 3? 1 minus 4 equals negative 3. Doesn't it make sense that I have the 10 compared to the 10,000? Is the 10 scaled down by 10,000? That through division of the numbers, I decrease the magnitude. So it makes sense that if I'm dividing inside, then I can rewrite that as a decreasing outside. Yeah, go ahead. So notice we've now got this connection between division and subtraction. Subtract magnitudes whenever I divide by things. What about this last one? If I do log of 100 squared, that's going to be the same as log of what? 100 times log, well, not times log of 100, but I'll give you that it's 100 times 100. Because I'm just going to repeat it exactly as I see it. How many zeros will that have? 4. How many zeros did each 100 have? 2. Doesn't it make sense that I doubled the number of zeros because I repeated the 100 twice? Do you see how this does make, like, it's a story. It's approachable. Two times of the number of zeros in the 100. So it's like, oh, maybe if I have an exponent, I can bring that to the front because I'm going to have that many repeats of the zeros because I'm going to have that many repeats of the magnitude. Let's start to use this as a way of checking for some other formulas because I don't remember these. Like, I remember some of them because I've used them a bunch, but in all honesty, I just figure them back out. Like, for example, is this true? I don't know. Let's figure it out, shall we? Let's choose some good numbers. Like, let's do on the left side, let's just try something. Log base 10 of 100 is 1 divided by log base 100 of 10. Right? I'm just going to try some numbers. You all tell me, log base 10 of 100 is 2 zeros, right? Does it make sense that we have 2? Let's double check over here. Log base 100 of 10, that's a little bit rough to do with zeros. Let's do a power finder. What's the power that turns 100 into 10? That would be 1 divided by 2 repeats. That'd be too many on the bottom. 1/2. It's a square root, isn't it? The square root of 100 is 10. So wouldn't it make sense that 2 is equal to 1 divided by 1/2? In other words, if you flip your perspective, doesn't it make sense that instead of multiple multiplications, you now have parts of multiplication, which we call roots, square roots, cube roots, 10th roots. So yeah, this is true. Not because I found one data point that supports it, but because the story does make sense no matter what I think about. Repeating multiplication is going to be the same as undoing a bunch of repeated division. Go ahead.
So how does 1 over 1/2 turn into 2?
Because I could think of this, if you'd like, algebraically as the fastest way. I could scale both sides up, and that would get me 2 over 1. But you can also do it by a story of saying if I have 1 cookie and I split it up into halves, I now have 2 halves. Or split it up into halves, I now have 2 pieces. Let's do this one. Is this one true? Again, let's just try some numbers, right? Gain some insight, and then we'll try to put a story to really back it up. Let's do, looks like log base 100 of 10 plus 10,000. And ask ourselves, is that the same thing as log base 100 of 10 combined with log base 100 of 10,000? Well, real quick, On the right-hand side, this is going to be what? There we go. So let's check the last one. What power turns 100 into 10,000? 2. And doesn't that make sense? Because I had 2 zeros, and now in terms of that, I have double to make 4. So I have 2 zeros here, two groups of 100, 2 magnitudes of 100. What about 100 to 10? We already explored that that is 1/2. Is 1/2 plus 2 the same thing as the number of zeros in, what would that be? 10,100. Like, no, that's only a little bit bigger than 10,000. That's not going to quite, like, that doesn't quite work there, right? Like, there's not that many. There's not 2.5 doublings of the zeros in that. Like, that doesn't work. So this is how we know that that is false. So we're not just aimlessly pushing the symbols, we're checking it in terms of magnitudes. And then we're reminding ourselves that we could have done this in computer language. We could have done this in ancient Arabic language of counting numbers. All of those would be fine because I'm just building magnitudes or taking magnitudes away. What about this one? I'm just going to do it briefly. We're not going to do it with the zeros. Let's talk it out. If I multiply, am I going to build zeros? Let's check. 10 times 100, is that going to build zeros? Good. So then the left thing's going to build some zeros. How's it going to build the zeros? Are we going to just squish, like we're just going to have the zeros of one combined with the zeros of the other, right? There you go. That's what's in front of us. That if I wanted to look at the zeros after multiplication, the magnitudes after multiplication, it's going to be the magnitudes of one combined with the magnitudes of the other. Yes, this is true. Go ahead. Last one was false. Last one was false. Which is why it didn't matter that I had a typo in it. It was going to be false either way. What about this one? Does it make sense that if I raise something like 100 squared, that I'm going to double the number of zeros? If I made it to the third power, would it triple the number of zeros? So depending on that exponent, it's going to be that many times of the original zeros. That's how it works. What about this one? Maybe this one is a little bit better to explore through power finder lens. Find the power that turns B into 1. That power would be 0. There you go. So this one's true. And does it make sense that if I wanted to figure out how many zeros there are here, there are no zeros. So that also works too. It doesn't matter. You got to keep the mask up for me. Quotient formula. If I divide something with lots of zeros by something with few zeros, will I get less zeros? 10,000 divided by 100 makes less zeros? There you go, true. That's what it's saying. It says I take away zeros when I do division. That makes sense to me. What if I ask what's the power that turns B into itself? 1, because 5 to the first is, and 10 to the first is, there you go. You don't have to memorize these. But if you'd like, you can go through, and in the guided notes, I've drawn parallels, because we do know that the power finder function is just trying to find the power. So it makes sense that any patterns we had from Monday's class are going to have parallel patterns here. So if I was able to multiply the bases and add the exponents before, now maybe I have something similar in terms of the logarithms. So if you have any questions on this, feel free to stick around. Give this one a shot if you will. Remember that if we're multiplying the argument, that's the same thing as adding magnitudes. So if we're going from the inside out, we can try to make that an expression of addition. All right, I'll be around if you have any questions.